Greetings. We're back, and in this video I'm going to talk about what happens when you put capacitors in parallel and in series. That's going to necessarily give you a different value of capacitance than you had had previously. So let's take a look at the case where we're in parallel first, and that's the same as the PowerPoint slide that we're on right now. Conceptually, I want to go through this. Now imagine I redrew this parallel capacitor. Instead of looking like this, I could say that it actually could be the two capacitors right near each other, separated by a small distance right there, and that I put the wires so that they're connecting these two metal plates right here. I'll do the wires like this. There's one wire there, another wire there. Electrically, these would be the same because everything over here that's purple is metal, and everything over here that's purple is metal, and all I'm doing is bringing these two plates closer to each other and making the wire connections closer. But as far as we're concerned electrically, the situations are identical. Now I can further redraw this and say that it looks more like this, or just like this, where I have two metal plates with wires coming out of the center of them on each side like this. And I can say that this is equivalent to this or that. Now when you compare these, you could say, well, this capacitor is basically just those two plates kind of attached together. So basically you have plates that have a bigger area in this case than you had in that case. And since you know that the value of capacitance gets bigger by this equation here that we came up with in the last video, it's like this: capacitance equals epsilon 0 times A divided by D, where A is the area of them. You can imagine that this capacitor here, which represents the parallel combination of these two, is going to have a larger value than either of the other two. Conceptually, that's what's going on, and the spacing between them is the same, so the D is going to be the same here as it is here. Let's take this a step further and actually calculate what the capacitance will be if I put two different capacitors in parallel. So I'm going to redraw this situation, and well, I'll draw it up there, and what I'll put on here to remind you, I'm going to give you the equation for capacitance. This one, Q is equal to Chula Vista. That's the one I can remember because I like remembering Chula Vista. And I'm going to say that this is C1 and this is C2. And that C1 has a minus Q1 on this side and a plus Q1 on that side. And that C2 has a minus Q1 on this, Q2 on this side and a plus Q2 on that side. So that means that there's a voltage across each capacitor. Now, if this were class, I'd ask you a clicker question. I'd say, which of these capacitors, C1 or C2, has the greater voltage across it? Let's say C2 is greater than C1. Which one would have the greater voltage across it? Pause the video, see if you can answer the question, and I'm going to answer it right now. Because these two capacitors are in parallel, they're both going to have, I'll say this one is V1, and this one here is V2. I'll say that V2 has to equal V1 because they're in parallel. The reason is if I go uphill here, I have to go back downhill here by the same electrical potential to come back to the ground level here. This is ground, this is the mountaintop. Whether I go up this way or whether I go up that way, it has to be the same potential difference. So they're going to have the same voltage across both capacitors. Great. So rather than calling them V1 and V2, I'm just going to call them V. All right? Now what about the charge? What can I say about the charge? Well, I can't say the charges are necessarily the same. They could be. If the capacitors were the same value, then the charges would be the same. But the charges are going to be constrained by the value of the capacitance. So the capacitor that has the larger capacitance, if C2 is greater than C1, then Q2 is going to have to be greater than Q1. You can see that from this equation, because the V's are going to be the same in this case across both capacitors. Let me show you another way to think about this is whatever charge here, Q1, that exists, add that to the charge here, Q2, and that's going to be the amount of charge that's on Q3. You can think about that also. So I'm going to say if I were to draw the equivalent capacitor here, I'll call it C3, which represents the parallel combination of these two. C3 has to have on its left plate minus Q1 minus Q2. So I could say it's minus Q1 plus Q2. And on its right plate, it has to have plus Q1 and plus Q2. or plus Q1 plus Q2 on this plate here. Okay, so these two charges are going to have to add together to be the charge on this capacitor, which would be Q1 plus Q2 on that plate, and Q1 minus Q2 on that plate. Okay, that's what Q3 is going to be. So I could say this, I could say Q3 equals Q1 plus Q2, and Q3 is also equal to C3 times V, because what voltage is going to be across this equivalent capacitor here, which represents the parallel combination of these two, has to be the same voltage that was on either of these two. If I put my meter here, measured negative side here, positive side there, I get a voltage V across this capacitor here. And that's what has to be the voltage across capacitor C3. So I'm going to calculate this now. I'm going to say, okay, C3 is equal to Q3 divided by V, and Q3 is equal to Q1 plus Q2, the sum of the charges, divided by V. That's what C3 is going to be equal to. All right, take this over to this side here. So if C3 is equal to that, should be Q1 by the way, it's also equal to Q1 over V plus Q2 over V. But what's Q1 over V equal to? This is equal to C1. This is equal to C2. So when I put two capacitors in parallel, the equivalent capacitance is equal to the sum of the two capacitors that I'm putting in parallel. That's when you have parallel capacitors. Now I'm going to do the case for series capacitors. But I'll leave my original equation for capacitance up top here. Let's start off with the conceptual idea behind series capacitors. Let me put two capacitors in series in front of you here, C1 and C2. C1, C2, and I want to put them together to get C3. So in the end, I'm going to have C3. How do I do that conceptually? Imagine this. This here is going to have some charge on it. Let's say it has minus Q over here, plus Q over there. I'll call it Q1. How about this one? I'll say, oh, this has minus Q2 and plus Q2 across it, like that. So this side is minus Q1, that is plus Q1. This is minus Q2, that is plus Q2. And I have these two capacitors that are in series with each other. What does that look like? Well, imagine this here. I almost think of this as like an island. Think of this as ocean, and that is ocean, and there's an island here. That island has to be neutral. There's no charge jumping across this at any point. Charges come and go on the capacitor, but whatever comes on one side has to be equal on the other side because it has to be net neutral in the middle. There's no way that you can get charges jumping across here so that this is net positive or net negative. It's got to be neutral. So I could draw it like this. I could say, okay, well, that tells me one thing. That tells me that this charge here has to be the same as that one there. In other words, plus Q1 has to be equal to minus Q1. Minus Q2. So therefore, Q2 has to equal Q1, which tells me that this Q2 also has to be Q1. So basically, when capacitors are in series, the charge on one has to be equal to the charge on the other. That's going to be really useful for us. All right, and so now I can redraw this like this. I can imagine this like this. I'm going to make that island really small. So this is C1, this is C2. I'm basically shrinking this down. This is net neutral. This is minus Q1, and this is plus Q1. And then I could take it one step further and say, oh, I can go a little bit more here. And I can say, oh, I can make that island completely go away. And say it's because it's net neutral. It's not really doing anything for us there. So what I have here is this side here. This is minus Q1. And over here, I'm going to have plus Q1. And you may say, wow, this looks really wide. I did that purposefully. This here should be the width of this plus that. Notice this is so much wider here. The island goes away, but the spacing between these two does not go away. That's important. That sets the value of the capacitance. And since the equation for a capacitor, for a parallel plate capacitor, is this, when D gets bigger, the capacitance goes down. So you might expect when I put capacitors in parallel that the equivalent capacitance is going to be smaller than it had been previously, which is what you saw in that last lab you did before we were forced to have the break, I should say. All right, I'm going to take this to the next step in the next video. There'll be just one more video in this sequence for Tuesday's lecture.